below figure. Determine the natural frequency of spring mass system shown in the below figure. The figure is as follows. This is the radius r and it is moving in this direction. Here we have attached one mass and here is the spring which is fixed here at the bottom, and this mass moves in downward direction, that is shown as x. The spring is having a stiffness of k. So for this system we need to find out what is the natural frequency for this given system. Let the total energy solution, let the total energy of the system, let the total energy of the system is given by the total energy. I am going to represent it as T. So this total energy for this particular system, that is a spring mass system, is equal to kinetic energy, is because of kinetic energy of mass small m, that is one thing. Then kinetic energy of pulley. So here is the pulley, so it is represented by m. Kinetic energy of pulley, pulley, this is a capital M, plus the potential energy of the spring, plus potential energy of spring, which is given by K. The total energy for this system is given by T, and T is equal to the kinetic energy of this mass plus kinetic energy of this pulley M and potential energy of spring K. So how to represent or substitute the values for the equations, that is a T equal to kinetic energy of mass M. So it is given by half into m into x dot square, that is the kinetic energy. We are going to give it as half into m into v square. So v is nothing but velocity, and velocity is represented by x dot, displacement as x, and acceleration as x double dot, plus as it is having a linear motion, so it is half into m into x dot square. So now kinetic energy of pulley, so how it is going to move? So it moves through an angle theta. So if this is the pulley, so it moves through an angle theta. So what is the displacement? Displacement is x is equal to x is equal to, so it moves through a radius r through an angle theta. So it is r into theta, that is x for the spring, that is a half into k into x square, that is x is equal to r into theta, that is for potential energy of the spring, that is k. And then coming to the kinetic energy of the pulley. So kinetic energy for this circular element is given by half into I into theta dot square plus potential energy of the spring, that is k, half into k into x square, half into k into x square. So now we need to represent what is x and what is x dot. So what is x? X is nothing but it is the displacement. So how much displacement it is going to take place? X is equal to r into theta. R is the radius and it moves through an angle theta. So x is equal to r into theta. So I will represent t half into, what is the value for x dot? X is r into theta, and what is x dot? R into theta dot square. So x is equal to r theta and x dot is equal to r into theta dot. So what is x dot square? So it is r square into theta dot square. So t is equal to half into m into r square into theta dot square plus half into I into theta dot square plus half into k into what is x? X is r into theta. So r square into theta square, which is equal to constant. Because in case of energy method, we have seen that T plus V is equal to constant. T plus V is equal to constant. In case of energy method, we have done this. In the previous classes, we have discussed this. Once again, you can go through the notes and you can go through the videos. So we'll get why we have taken it as a constant. So moment of inertia of pulley. So how to write it? The moment of inertia of pulley that is I is equal to half into m into r square. The so we are going to remain with m r square plus I. I is nothing but half into m r square. You can substitute the value of I here, or you can keep it as it is, and you can substitute the value of I here also. Is it clear? It is not necessary that you have to substitute here. You can use I here also. So what I have done is I have used only I here. So this is for your understanding purpose. You can substitute half m r square also, or you can keep it as I only. So when you remain, or when you come with this equation, you can substitute I, or if you substitute half m r square, there will be a little bit change in this equation. Is it clear? So m r square into half m r square into theta double dot plus k r square into theta is equal to 0. So comparing this with theta double dot plus omega n square into theta is equal to 0. So you can find out the value of theta or omega n as theta double dot plus k into r square divided by m r square plus half into m into r square into theta is equal to 0. So therefore I can find out the value of omega as under root of 2k r square divided by m r square 2m r square plus capital M r square, or in terms of radian per second. So this completes the given problem statement. So once again I will explain. So this is our given system. For this given system, what is the natural frequency we need to find out? So this is a spring mass and pulley system. So how to write the total energy? The total energy is because of kinetic energy of this mass m, then kinetic energy of this pulley m, and potential energy of this spring. So we know what is the kinetic energy equation, that is half into m into v square. So v means what? It is velocity. So velocity is represented by x dot. So I have written it as half into m into x dot square. Then kinetic energy of pulley. So it is a circular element. So it becomes half into I into theta dot square. So this is theta dot plus potential energy of the spring is given by half into k into x square. So what is x now? So how to find out what is x? X is the displacement. So how much displacement it is going to take place? It is going to take place a displacement of r into theta, because r is the radius, theta is the angle through which it is displaced. So total displacement is r into this theta, that is x. X is equal to r into theta. So what is x dot? R into theta dot is x dot. So wherever you have x and x dot, substitute the value of x on x dot. So that is T is equal to half into m, x dot is r into theta dot, so r square into theta dot square, plus half into I into theta dot square, plus half into k into x is r into theta, so r square into theta square is equal to constant. So kinetic the moment of inertia, I is moment of inertia, and that is of pulley. The moment of inertia of pulley is given by half into m into r square. If you want, you can substitute the value of I here only, or at the end also you can substitute the value of I. So now I will understand what is the value of I, and I am not going to substitute it, and I am going to differentiate this equation with respect to time. So what I am going to get? So this half into m into r square into 2 into theta dot into theta double dot. So this 2 and 2 gets cancels. So remaining is m r square theta dot into theta double dot. Then the differentiation of this half into I into 2 into theta dot into theta double dot. So 2 and 2 gets cancels. Remaining term is I into theta dot into theta double dot. Then next half into k into r square into 2 theta into theta dot. So 2 and 2 gets cancels. So remaining term is k into r square into theta double dot is equal to 0. So now so everywhere we have theta dot term. So I can remove the theta dot term. So the remaining equation will be m r square theta double dot plus I into theta double dot plus k r square into theta. Now taking theta dot term as common, that inside the bracket remaining will be m r square plus I into theta double dot. So what is the value for I? I is m into half into m into r square. So I have substituted the value of I, that is half into m into r square plus m r square into theta double dot, which is common, plus k r square into theta is equal to 0. So comparing this equation with theta double dot plus omega n square into theta, so what will be the final equation for omega n? The value for final omega n value is 2k r square, because this 2 goes on the top. So 2k r square, multiply this with 2, this with this. So if I take the LCM, then it will be 2 m r square plus half m r square divided by 2. So this 2 goes to the top, and it is 2k r square plus 2 m r square plus m r square radian per second. So this completes the fifth problem on determining the natural frequency of a spring mass system. So let us solve the another problem, which is little bit same and little bit different to the previous problem whatever we have solved. That is the problem number 5. take down the next problem. That is problem number 6. Find the natural frequency of the system shown in the figure. The problem statement is find the natural frequency of the system. Find the natural frequency of the system shown in the below figure. So it is a little bit different compared to the previous problem. So here we have two pulleys. The mass is attached to the inner pulley, which is having a radius small r, and the spring is attached to the outer pulley or big pulley, and it is having a radius of capital R, and the spring stiffness is K. The spring stiffness is K. Let x2 is equal to the deflection of the spring. Let x2 is equal to deflection of the spring. So what is the deflection of the spring? That spring is attached to the bigger one or the bigger pulley which is having a radius of r, and it moves through an angle theta. So the deflection of the spring is r into theta, which is nothing but x2, and that is going to represent deflection of the spring, that is x2 is equal to r into theta. So therefore spring force, so what is the equation for spring force? K into x2, that is nothing but deflection into deflection of the spring, that is going to give the spring force. So it is K into r into theta, because we know what is the value for x2. So therefore spring force is given by K into r into theta. And what is x1? So x1 is the downward moment of the mass. X1 is the downward moment of the mass. So how much it is going to move? Downward movement of mass. X1 is the downward moment of the mass. So x1 is the downward moment of the mass. So how much it is going to move? It is going to move with a small radius r and inclination theta. So therefore x1 is equal to r into theta. So x1 is equal to r into theta. So therefore total kinetic energy is given by total kinetic energy. Therefore total kinetic energy is given by kinetic energy because of this mass plus kinetic energy of the rotating element plus the potential energy of the spring. So therefore total kinetic energy is equal to kinetic energy of mass small m plus kinetic energy of rotating element plus potential energy of spring plus potential energy of the spring. So what is the kinetic energy of the of mass? Half into m into x1 dot square, right? So half into m into x1 dot square, because kinetic energy is given by half into m into v square. So what is v? V is the velocity. Velocity is represented by x dot. But which x? That is x1 is going to represent the displacement for mass small m. So that is why it is half into m into x1 dot square plus kinetic energy of rotating element, that is half into I into theta dot square. So we know that whenever we get rotating element, its kinetic energy is given by half into I into theta dot square. If it is a linear movement, then it is half into m into x dot square plus potential energy of the spring, that is half into k into x2 square. Half into k into x2 square. So we know what is x1 and we know what is x2. So substitute wherever you have x1 and x2 and x1 dot and x2 dot, substitute those values. We have x2 and we have x1 dot. So x1 dot, to get x1 dot value, you should have the value of x1. So we know what is x1. So we can find out what is the value of x1 dot, that is nothing but r into theta dot. So substitute the value. So half into m into r square into theta dot square plus half into I into theta dot square plus half into k into x2 square is r2 square into, what is the value for x2? r2 square into theta square. So we have substituted all the values. We have substituted the value of x1 and we have substituted the value of x2. So x1 dot is r square into theta dot square and x square is r square into theta square. So now differentiating this one. So d by dt of half into m into r square into theta dot square plus half into I into theta dot square plus half into k into r square into theta square is equal to d by dt of constant. D by dt of constant. So differentiating the equation with respect to time, so we are going to arrive with the equation, that is d by dt of half into m into r square into theta dot square plus half into I into theta dot square plus half into k into r square into theta square is equal to d by dt of constant. So after differentiating, we are going to remain with m r square theta dot into theta double dot plus I into theta dot into theta double dot plus k into r square into theta dot is equal to 0. So we are going to remain with m r square. The theta dot square differentiation is 2 into theta dot into theta double dot. This 2 and this 2 gets cancelled. So remaining term is m r square theta dot into theta double dot plus half into I into 2 into theta dot into theta double dot. So 2 gets cancelled. Remaining term is I into theta dot into theta double dot. And similarly here, half into k into r square into 2 theta into theta dot, 2 gets cancelled. The remaining term is k into r square into theta dot. So I can write m r square plus I into theta double dot plus k r square theta is equal to 0. So theta dot turning that side and it becomes 0. So comparing this equation with theta double dot plus omega n square into theta is equal to 0. So I can get the value of omega n as under root of k into r square divided by m r square plus I. I can get the value of omega n as k r square divided by m r square plus 1 radian per second. So I can find out easily what is the value of omega n. So once again I will explain how to do this. There are two pulleys. One is the smaller one and another one is the bigger one. The radius of smaller pulley is r and the radius of bigger pulley is k. the mass is attached to smaller pulley and spring is attached to the bigger pulley. In the previous problem, both mass and spring were attached to only one pulley. There was only one pulley, but in this problem, there is a addition. There is another pulley to which the spring is attached and mass is attached to another pulley. So x2 is the deflection of the spring. x2 is the deflection of the spring, and how much deflection it is going to take place? With a distance r and angle theta. So x2 is equal to r into theta. Therefore, spring force is k into r into theta. The next one is x1, that is the displacement of the mass or movement of the mass. How the movement of the mass is going to take place? In the downward direction. With a what will be the displacement? It moves with a radius r and angle theta. So the displacement is x1 is equal to r into theta. So therefore, x1 dot is equal to r into theta dot. So now what we need to understand, the total kinetic energy of the system is given by kinetic energy because of this mass, kinetic energy because of the rotating element, plus potential energy of the spring. So we know what is the kinetic energy of mass, we know what is the kinetic energy of rotating element, and we know what is the potential energy of the spring. So substitute all the values and differentiate with respect to time. So we can find out the value of omega n, and the value of omega n is found to be omega n is equal to k into r square divided by m r square plus I radian per second. So this completes the different varieties of problems. So almost we have solved around 7 to 8 problems we have solved on this kind of problems. And now let us move ahead and let us try to understand the new concept in the chapter. And the next one is very, very important, which has been asked many of the times. That is nothing but derivation we are going to do for critically damped, under damped and over damped system. So the next concept is the derivation of differential equation of damped free vibrations. Differential equation of damped free vibrations. Differential equation of damped free vibrations. So first let us take the figure for this. To this we have attached one spring, and here is the damper or the dashpot, we can call it as, and here I have attached the mass. So this the figure shows a spring mass dashpot system. So this is dashpot represented by C. This is a spring having a spring stiffness of K, and this is the mass M. This is the mass M which is in its mean position, and this dotted line indicates the mean position of the mass after a time interval of t. So this distance is x and this distance is delta. So take down, consider a spring consider a spring, consider a spring, consider a spring carrying mass at one end, carrying mass at one end. Consider a spring which is carrying a mass at one end. At this end it is carrying a mass and other end is fixed, and other end is fixed. Consider a spring having a stiffness K to which to the one end of the spring we have attached a mass and the other end of the spring is fixed, and the other end of the spring is fixed. Next, a damper is provided. A damper is provided. A damper is provided between the mass. A damper is provided between the mass and rigid support as shown in the figure. As shown in the figure. Consider a spring having a stiffness K. To the one end of the spring we have attached a mass and the other end of the spring is fixed, and in between mass and a rigid support there is a damper or dashpot, and which is mentioned as C. Let K is equal to stiffness of spring. Let K is equal to stiffness of spring. Let K is equal to stiffness of spring. C is equal to damping coefficient. C is equal to damping coefficient or damping coefficient. Omega n is equal to natural frequency. Natural frequency of underdamped vibration. Natural frequency of underdamped vibration. Natural frequency of underdamped vibration. X is equal to, which is shown here in the figure, displacement of mass X is equal to displacement of mass from mean position, displacement of mass from mean position at time t. X is equal to displacement of mass from its mean position after or at a time interval of t. X dot is equal to velocity of mass at time t, and x double dot is nothing but the acceleration of mass at time t. Kx is the spring force. Kx is the spring force. Mx double dot is the inertia force. Mx double dot is the inertia force, and Cx dot is the damping force. Cx dot is the damping force. So these are the terms which are involved in this particular case. And next, M is the mass suspended. M is the mass which is suspended from the spring. Weight is W is the weight of the body, which is given by M into G, and delta is shown here. That delta is nothing but it is a static deflection of the spring. When we attach this mass to the spring, there will be a deflection, and that deflection is shown by delta. the weight of the mass will be acting in the downward direction with an amount of m into g. Kx is the spring force, mx double dot is the inertia force, and cx dot is the damping force, which is because of the damper provided. Next, take down. Let the body be displaced by a distance x in the downward direction from the mean position. Let the body, which is shown here, the forces acting also, because that is also important. So first one is, what are the different forces? Mx double dot is the one force, Cx dot is the one force, and Kx is the one force. So in detail I am going to write accelerating force, in the direction of motion, accelerating force in the direction of motion. So which is nothing but m into d square x, m into x double dot, m into x double dot. The accelerating force will be acting in the downward direction. So I can show it here in the downward direction. Accelerating force in the direction of the motion. The direction of the motion is nothing but the downward direction, and that is mx double dot. The next, second one is the damping or the friction force. The next force acting is the damping or friction force. Damping or the friction force in opposite direction, of motion, that is nothing but in the upward direction. When this mass moves in the downward direction, there will be a resistance, or there will be a damping or friction force which will be in the opposite direction of the motion, and it is given by c into x dot, and it is in the upward direction. And third one is the spring force, which is given here. Spring force. Third one is the spring force in opposite direction, of motion, which is given by k into x, which will be in the upward direction. So when this mass moves in the downward direction, there will be a damping or friction force, which is nothing but c into x dot, which will be the opposite direction. That is nothing but the resistance for this movement in the downward direction, and also there will be a spring force in the opposite direction. This spring force will also be in the opposite direction to the motion of the mass m, and which is given by k into x. Next, take down. For dynamic equilibrium of body, the sum of inertia force, and the external forces in any direction should be 0. The sum of inertia force and external force in any direction should be 0. For this body to remain in equilibrium, the sum of inertia force in the downward direction should be equal and the external forces in any direction should be equal to 0. It means then only the body is going to remain in the equilibrium. The sum of downward force should be equal to the sum of the upward force, so that the body remains in the equilibrium condition. So if we add the downward forces and the upward forces, its sum should be equal to 0. Here the external forces are the spring force and the damping or the friction force. Here the external forces are the spring force and the damping or the friction force. The magnitude of inertia force is same as that of accelerating force. The magnitude of inertia force is same as that of accelerating force, but it acts in the opposite direction. So when this mass moves in the downward direction, there will be an equal and opposite reaction for this movement, and that will be same as that of mx double dot, but it will be acting in the opposite direction. So therefore the equation of motion can be written as, the equation of motion can be written as mx double dot plus cx dot plus kx is equal to 0, and I will call this as equation number 1. This equation can also be written as x double dot plus c by m into x dot plus k by m into x is equal to 0, and I will call this as equation number 2. So what I have done is, I have divided this equation by m, so that it remains as x double dot plus c by m into x dot plus k by m into x is equal to 0. A system having the equation of motion as given by the equation number 2, is said to be single degree of freedom damped vibrating system. So now how to find out the natural frequency for this? So let us understand. To find the natural frequency, to determine natural frequency, so how to find out the natural frequency? In that, substitute or put c is equal to 0, then what will happen in the equation number 1? If I substitute c is equal to 0, then what will be the equation? The equation is mx double dot plus cx dot plus kx is equal to 0. So if I substitute c is equal to 0, then what will be the remaining equation? Mx double dot plus kx is equal to 0. I can write this equation as x double dot plus k by m into x is equal to 0. So I can compare this one with x double dot plus omega n square into x is equal to 0. Now compare the coefficients of x double dot and x. So I can find out the value of omega n as under root of k by m radian per second. The value of omega n is given by omega n is equal to k by n radian per second, and I will call this as equation number 3. I will call this as equation number 3. We'll call this as equation number 3. The remaining things